Welcome. So we're going to continue a little bit more with our discussion about how to count and how to do arithmetic. Pardon me. So a couple of things I just want to talk about. The first strategy is actually a really wonderful thing called counting on. And this is actually a good place to employ things such as your fingers. So if you're talking about kids, one of the things they probably do is if you do, for instance, 5 plus 3, like we have here on the screen, they would hold up 5 fingers on one hand and 3 fingers on the other hand, and then they would count 1, 2, 3, 4, 5 with the first hand, and then 6, 7, 8. Well, they get 8, which is the correct answer. However, the problem is that limits them for several reasons. That lets them only be at up to 10, and in addition to that, they have to recount the whole time. Another way is this counting on strategy. So just to make it a little more clear, I'm actually going to stop my video for a second. I'm actually going to turn my video back on. If you look up in my video, just have on the side, the video is that if I'm counting this, instead I go, okay, I have 5, and I have 5, then I go 6, 7, 8. So I start with 5, and then I just start counting after that. This is a great thing to do with kids, and it's a great way to help them to actually see the numbers and so forth. And that way I could say, like, what is 5 plus 8? Well, 5, 6, 7, 8, 9, 10, 11, 12, 13. 5 plus 8 is 13. So this is the way that we can kind of get that going and kind of look at it a different way. All right. I hope that visual kind of helps you a little bit. Let's go to our next strategy, which is called doubles. Now, counting by doubles is actually a very common strategy that's usually employed in, I actually have seen it starting in kindergarten, usually in 1st and 2nd grade, where you start just looking at all the specific doubles. What's 1 plus 1? What's 2 plus 2? Plus, and so forth. And then, as it's mentions even on the slide, something that's really, really important is that we then start looking at what's doubles plus 1 more, doubles plus 2 more. So, and this is an example I've seen in a textbook, is 6 plus 7. Well, 7 is just 1 more than 6. So 6 plus 6, that's double. I know that one's 12. So this is 1 more, 12. Next one is 13. Now, this idea of doubles plus 1 and doubles plus 2 tends to be a bit harder for a lot of kids, but it does really build on this idea of doubles, and doubles, or counting even by 3s, counting by 4s, all those things really help kids get comfortable with not only addition, but then multiplication when we get to multiplication. We'll get there, don't you worry. All right. Let's talk then about making 10. So this is another really good strategy. And to kind of demonstrate this is we're going to literally make 10s out of something and then add the remaining. So I'm just going to show you here on the screen. If I had something like, say, let's go 8 plus 5. Well, again, I know that 8 only needs 2 more. So if I do 8 plus 2, but if essentially I'm breaking the 5 into a 5 is 2 plus 3, and I know that this is 10, and 10 plus 3 is 13. So this idea of actually getting it close, it's a very good manipulative process. It lets students work with nice numbers, because I think most students actually love doing stuff like, what's 10 plus 3? What is 20 plus 3? 20 plus 7? Those sort of situations are very, very easy for students to work with. However, this requires them to be able to do things such as in this example where I have 5, and I'm essentially breaking it up into 2 plus 3. That idea of taking 5 and breaking it apart requires them to be familiar about what number combinations can 5 break into. 8 plus what is going to make 10. So this strategy, while it gives you really, really nice numbers, and it can be really wonderful, it usually is not an introductory strategy. It's more of an advanced strategy, but it is actually really, really good. And I'll show you a little bit later how we can use a similar idea even for larger numbers like hundreds and so forth. All right, let's go to our next slide then. Let's talk just about some general properties that are really, really important. The first of which is called the commutative property. The commutative property means literally, if I add two numbers together, the order in which I add them does not change. So if I'm adding 5 plus 3 or 3 plus 5, it's exactly the same thing. This ability to add them in whatever order we want can become very useful later on when we have multiple numbers to deal with. We can reorder them as we want. Now, this only works if there's addition. If we have negative symbols and other things, again, we'll talk about order of operations later, but those things will start playing a role in messing with things. All right. Another key property is called the associative property. So if I have A plus B plus C, I can figure out which two. Even in a computer, they don't add all three at the same time, or a calculator. Your calculator is even told to pick two, add those, and then pick the next one. It's really not like super beyond what you do. It's just doing it, and we're not thinking about what it's doing. So when you have a set of numbers, this ability is really, really nice. For instance, if I did something like, let's say, 3 plus 4 plus 6. Well, 3 plus 4 is 7, right? But if I rewrote this as 3 plus 4 plus 6, again, this adds up to a really nice number, 10. 10 plus 3 is 13. This is a lot easier to do than if I tried just doing 3 plus 4, making 7, and adding that to 6, and still getting the same spot, even though we've done this a couple times. My apologies, minor technical glitch. All right. Let's talk about the next property. It's called the identity property. It's the fact that any number plus 0 is that number. 0 is the number that I can add to any number, and it does not change the value. Because that 0 is called the additive identity. Now, is that a technical term that you really, really need to know? No. But the idea that there's something that I can add and it does not change the value is a really important idea. And this is why 0 is so important when we start talking about numbers and how we add them together. Now, just a quick example again to show this, the commutative property, 6 plus 8 is equal to 8 plus 6, and 3 plus 6 plus 9 is the same thing as 6 plus 3 plus 9. Now notice, the second problem, all I did different was I simply reordered, I reshuffled 3 plus 6 into 6. And the last one, took 8 plus 5, and I took the plus 2 and I switched it to this side, and then I regrouped 8 plus 2, then plus 5. So all these are using using commutative properties and associative properties, lots of different things all involved. All right, so let me move on from these properties. Let's talk about some basic algorithms that will come up. So the first, and this is where we start getting to blocks. So these are called 10 blocks, in case you've never seen these. These are, again, very, very useful, especially in the classroom, you can have these. Kids often are taught, I'll just tell you a real quick note, and I'll draw it on the screen. They're often taught to draw a line to represent one of those sticks and put a dot to the dots represent the individual blocks, whereas this thing is that big block. So they do this. Now, so again, what this is one is simply doing, if you examine it closely, is we have 14, a 1, and this. And then we can add them together by simply saying, okay, how many ones do I have? 1, 2, 3, 4, 5, 6, 7. There's a 7. How many big ones? 1, 2, 3. So that's 37. This is great, especially so they can visualize and see this idea of grouping and adding, like we mentioned before. It becomes a bit cumbersome sometimes with very large numbers, except that we then, if we have 10 of these lines, we make that into the block. That becomes a little bit easier. So again, this is very useful as we kind of move on. What about, so what if we do this? Two other common algorithms are called the expanded algorithm and the standard algorithm. Now, expanded algorithm, it's drawn vertically here, but I'm going to do it horizontally below so you can see what it really looks like as well. So if I was to write 14 plus 23, that would be equal to 10 plus 4. That's 14. So 14 gets me here. Plus 20 plus 3. This becomes this. Now I can reorder that to be the 10 plus 20 plus 4 plus 3. So I just used the commutative property. I rearranged the order in which I added them together. And now we can add the 10s together and the 1s together. And the 10s give me 30 and the 1s give me 7. The standard algorithm is when they're taught to literally just add straight down. Now, you can do it vertically by simply saying, what is 3 plus 4? That's 7. And then do these and write them on a line below. And notice you bring the 0 down because these are 10s. So we have to acknowledge that. This is a great way to reinforce place value, another teak that is out there, and kind of hit it up a little more. All right, let me clear that off. It's getting a little messy. But again, the standard algorithm, you're just going to add straight down. 4 plus 3 is 7. 1 plus 2 is 3. And we get this. This is the one that maybe you all are pretty darn familiar with. What happens, though, when we have numbers like this, 37 plus 28? Well, the expanded algorithm still now works really beautifully because I can still do 7 plus 8, and that's going to give me 15. And then I do 3 plus 2, or which is just 30 plus 20, which gives me the 50. Because remember, those are in the 10 spot, so they go right here. Sometimes I see this and they don't include the 0 there. They just have the 5 shifted over. Including the 0 really helps establish this idea of place value. And that it's not just a 5, it's 50. All right. So this is the great way to do this. Now, many of you probably are like, I didn't do it that way. I will tell you right now, there's actually a lot of texts and a lot of teaks that actually ask students to do stuff using the expanded algorithm. So expanded algorithm means you break it into the 10s, the 1s, the hundreds, the thousands, break in those individual parts, and then you can regroup them accordingly, which fits that visualization. To go back just a couple slides here, that's actually what these are the 10s, these are the 1s. So visually it connects for the students and they can kind of understand what they're going through. All right, now what about, I went slide too many. What about the standard algorithm? This is the one you probably many of you have used. And you go 7 plus 8 is 15. So you put a 5 here and carry a 1 up here. Now, one of the downsides, well, this is the one that's been taught for years. And I will admit, this is what I did for a long, long time. And then I started realizing other strategies and I utilized them. And some of my teachers really loved that I utilized them. In fact, I will tell you right now as a teacher, do not discourage any one of these. But you might simply say, I like that one because I'm simply more familiar. And that is a major downfall when we rely too much on just one of them and not on all of them together. If we do this with this kind of thing, the question for a student is, what's the 1? And is it easy when they write the 5s, or they sometimes forget the 1 or forget a 2 or forget it something else? While this is nice, it does get lost sometimes. So sometimes we were like, that's really easy. Now, though, you have to do 1 plus 3 plus 2, and I got to keep track of that. So again, warning, it's not always as clear as we want it to be. Now, you can still do this with this kind of addition if I have a bunch of blocks. So consider for a second, oh, sorry, wrong button. If I did 186, here's 186, plus 127. Well, what we do, as is indicated by the dotted grouping, is we figure out, well, 10 of these is equal to one solid block. And so I take those out, and now notice I'm just left with three more. So those three end up in that spot right there. Now what we do is, for the next, is now that we have all these, notice I now have 10, this dotted area right here, we have 10 of the, so these essentially are going away and being replaced by a 100ths block, and that's where the next one comes. And notice I have one left over, so it gets thrown in here. It's kind of leftovers. And then last but not least, we then have 300, so it's 313. Now, the downside, even as it's drawn right here with showing the ones above the numbers, is it can be kind of confusing where there's placed. And see, this one right here is actually placed in front of the kind of the front side of the 8. So the question is this supposed to be 11 or is this 1? There's a lot of things like this where we make notations, and sometimes it actually can be very, very confusing for the students, which is one of the reasons we generally try to avoid them. All right, another strategy that's actually different, you may have not seen, is what's called the left to right strategy. So many of you have probably learned to add from right to left of the numbers. So we often start with, I'm just get my nice spotlight. We often are adding up the ones first, and then the tens and the hundreds. We can do the other way. So 5 plus 7 is 12, and I give 2 zeros because there was 2 spots after it. 6 plus 5 is 11, and then again, there's 1 spot after, so I put a 0 there. And then 8 plus 7 is 15, and now I can literally add straight down 0, 0, 5, 0, 1, 1, 2, 2, 1, 3, and 1, 1. I will tell you this strategy, which is also called the partial sum, is a really nice way to organize things, and it really requires students to understand place value, which is one of the reasons it's a beautiful sort of situation. All right, let me toss at you another one. This is called the lattice algorithm. So the lattice algorithm, we have 3 plus 5 is 8. So there's no 10s and there's an 8. 5 plus 6 is 11. So I put a 1 right here. That's for the 10. And a 1 right here for the ones place of 11. 6 plus 7 is 13. So there's a 1 in the 10, 1 in the 3, and 7 plus 8 is a 1 and then a 5. And now you just add diagonally. So 5 plus nothing is 5. 1 plus 3 is 4. 1 plus 1 is 2. 1 plus 8 is 9. So this kind of organizes it in a way that kind of makes sense for a lot of people to understand and to see how on earth they can kind of do this to, again, make these numbers work to their advantage. And they're not confused about where that 1 is. It's up above that maybe they missed or overlooked. It's staring them in the face. They're always just adding 2 numbers at a time. That makes the process a little bit easier. Again, your brain does not really add 3 numbers at one time. It adds 2 of them and then adds the third one in. Same with the calculator, same with the computer. There is no such thing as lots of addition in the same exact moment. All right. I'm just going to throw a couple more quick ones to kind of wrap this up. So I want to talk about something called the opposite change algorithm. This one's kind of interesting. It says, decide which addend is closer to a nice number, and then decide how to adjust the addend so that it ends up as 1 or more zeros. Okay. What does this mean? Well, let's do an example. Let me write a number right here. So I'm going to do, let's say, 85 plus 27. Well, 85 is really, really close to 100. In fact, 85 plus 15 more gets me to 100. So the fact that I can get to 100 really easy is kind of nice. And so I can actually do this and then say, well, if this is 15, well, I got to take 15 away from 27, and that will leave me with 12. Well, this gives me 100, and this plus 12 is equal to 112. All right, let me do this using the same strategy, but a different choice of numbers. So this is where this one gets funky, is you get to choose, and as a result, it's not as algorithmic and clean. It actually becomes more creative. Well, let's look at 27. 27 is really close to 30. So I'm going to rewrite that as 30. But in order to get this to 30, I had to add 3 to it. Well, addition, I got to keep that balance. So if I add 3 to 1, I actually have to subtract 3. I don't know why that just doesn't. I have to subtract 3 from the other one. Well, what's 85 minus 3? Well, that's 82. And now I have 82 plus 30. Well, 8 plus 3 is 11. So that's going to give me, real quickly, just 112. So these are the ways that we can do this. This is kind of the idea that actually it's a very good mental math strategy and very, very wonderful. I'm going to end there. There's actually a ton more strategies we still go through, but these are some of the biggest ones, honestly. I've seen this opposite change one a lot. I've seen that left-right method. I've seen the expanded form a lot. I recommend you kind of have to work with each individual student, and it also comes down to what grade level you are. If I'm talking kindergarten, I'm not doing a lot of 2-digit stuff, and I'm probably actually going to do a lot more opposite change because you're going to get stuff close to 10, which is their fingers, and it feels really, really nice and easy then. If I'm talking about 3rd or 4th or 5th grade, I actually might really add some of these in because it gets them into recognizing what are some easy numbers to work with and how do we change numbers to get there. So they feel more capable of manipulating and modifying them to look the way they want them to. And that's really the big thing. All right, let me know if you got any questions about addition, and good luck.